So the last few questions, we're talking about galvanic cells. Some standard electrode potentials given below. Write the cell diagram of the cell formed by combining Fe3 plus Fe2 plus and Ce4 plus Ce3 plus half cells. So these are the reactions we're interested in. We've got Fe3 plus and Fe2 plus. That's a reduction, plus 0.77, so kind of wants to be reduced. Then we've got the cerium 4 plus an electron going to 3 plus. Again, reduction. Really wants to be reduced. Now, anytime you've got a cell, you've got to have a reduction and an oxidation, and we've got to therefore flip one of these equations to turn it into an oxidation. Okay, now the rule that we talked about earlier is that you flip the more negative one so that you end up with an even more positive EMF. So that means we're going to flip the ion to turn it into the oxidation. So the ion's going to be an oxidation after flipping. The cerium is going to be the reduction. So there we are, nicely flipped. Putting first of all, we want the standard EMF together. Well, the reduction is 1.45. The oxidation is minus 0.77. Put them together and plus 0.68 volts. And now we want to write the cell diagram. Well, the cell diagram, you always put the oxidation on the left and the reduction on the right. So there's the Fe2 plus to Fe3 plus. There's the Ce4 plus to Ce3 plus, separated by the double line. Now, because what we've got here is solution going to solution, there's a comma between them. Solution going to solution, there's a comma between them. And of course, in any cell, you not only have to have stuff in solution, you have to have a solid electrode. You can use graphite for that solid electrode. However, the A-level boards like to use platinum because obviously they think schools have got tons and tons of money to buy electrons. So there we are. The oxidation, 2 plus iron 2 plus going to iron 3 plus. The reduction, cerium 4 plus going to cerium 3 plus. Overall EMF plus 0.68. And there is the half or the full cell diagram. Diagram below shows the apparatus used to measure the EMF for Cu2 plus Cu and Fe2 plus Fe electrochemical cell. Some standard electrode potentials always also given. So first of all, name the part of the cell labeled A. That's the salt bridge. It's there to complete the circuit and also maintains charge balance because as one side loses electrons, so in other words losing negatives, some anions coming from the salt bridge to make that up, and then the other side is going to gain electrons becoming more negative, so therefore the cations from the salt bridge go to that side. Now, which of these electrodes would be positively charged in the above cell? You've got to, if you've got a cell, have not just a reduction, and both of these are reductions, but you have to have an oxidation as well. So in order to determine which one will be the oxidation, we take the one that is the more negative. Okay, now the one that is the more negative is of course the iron. So therefore that iron becomes the oxidation, and that tells us that's happening at the anode. And if the iron is the anode, that means the copper is the cathode. Electrons move from the anode to the cathode. So the anode, therefore, the anode is described as being the negative end, which means the cathode must be the positive end. So this electrode, the copper electrode, is going to be the positive one, and the iron electrode is going to be the negative one. Again, nice cell. Apparatus below used to measure the standard electrode potential for the Cr2072- and the Cr3 plus half cell. And this is, of course, the hydrogen electrode. Okay, hydrogen electrode is made up by having an acid, HCl, and then platinum electrodes. So those are A and B, respectively. Flow of electrons in the external circuit is going to be from the hydrogen electrode, which is 0, to the other one, which will have a positive, whatever reaction goes on in there, will have a positive voltage. Okay, C is of course the salt bridge. We talked about that in the previous question. Completes the circuit and maintains the charge balance. Same question, moving on. Concentration of both Cr2072- and Cr3 plus are 1 molar. So in other words, that's standard state. State and explain how the value shown on the high resistance voltmeter, I guess that's the V, would change if the concentration of Cr3+ ions were increased while the concentration of Cr2O7 2- was left unchanged. Okay, well, the reaction that's going on there is Cr2O7 being reduced to Cr3+. Okay, I'm not sure how you're supposed to know that other than knowing that dichromate is a really good oxidizing agent because it really wants to be reduced, which means it's got a positive reduction potential. So this is the reaction that is going on in this cell here. So if we increase the concentration of Cr3+, well, then that's going to drive the equilibrium to the left. If the equilibrium goes to the left, well, they're going to have not as much of the reaction, so it would reduce the voltage. All electrode potentials compared with standard hydroelectrode. Explain what's meant by that. So using the figure that we had for the last question, right? You've got hydrogen gas bubbling in there. You've got HCl in here. Okay, the reaction is 2H plus 2 electrons reversibly going to H2 gas, and the potential for this reaction is defined as 0. So therefore, if you've got the H plus and you've got the H2, then you've got a potential of 0. So therefore, whatever is in this other half cell, it's going to be the positive reaction that goes on, either reduction if it's got a positive reduction potential, or oxidation if you have a positive oxidation potential. Use platinum electrodes just because you can. You could use graphite just as well if you wanted to.